morning. This is Dr. Shankaraiah from Department of Physics. In this presentation, I am going to discuss about Module 1, which is crystal structure. So, in this, I have covered the structure and packing fraction of crystals in the earlier presentation. In this presentation, I will discuss the structure and packing fraction of body-centered cubic crystal and face-centered cubic crystal. Okay. So, we know that cubic crystal has three different types of Bravais lattices: simple cubic, body-centered cubic, and face-centered cubic. So, in the earlier presentation, I have discussed about the structure and packing fraction of simple cubic crystal, and now we will discuss about the structure and packing fraction of body-centered cubic crystal. Okay. So, the body-centered cubic cell has a lattice point within the cell in addition to the 8 corner lattice points as shown in figure. Okay. So, if you see this figure here, so this is body-centered cubic unit cell, right? So, there are 8 corners in this body-centered cubic unit cell, and in 8 corners you have 8 lattice points. Apart from these 8 lattice points, you also have a lattice point in the center, in the body, in the center of the body of this unit cell. Okay, so that is why this is body-centered cubic unit cell. If you do not have this body center of this, if you do not have this center point, this will become a simple cubic unit cell. Because we have this lattice point at the center of the body, this is called as body-centered cubic unit cell, right? Okay, so the first parameter which we are going to look at is unit cell volume, which is denoted by V. In case of cubic cell, all the edges of the cube are of equal length, A. So we know that in cube, all the lengths along 3 crystallographic axes along X and Y and Z. So if I say this is my X axis, this is Y axis, and this is Z axis, then all the axial lengths are equal in cubic unit cell. So A is equal to B is equal to C, and all the crystallographic axes are, all the axes are perpendicular to each other, right? So that is alpha is equal to beta is equal to gamma is equal to 90 degrees. So this is the condition for cubic unit cell, right? All the axial lengths must be same. So A is along the x-axis, B is along y-axis, and C is along z-axis. So A is equal to B is equal to C, and alpha equal to beta equal to gamma equal to 90 degrees. Because A is equal to B equal to C, the volume of this body-centered cubic unit cell is A cube. We have also find out that in the earlier presentation, the volume of the simple cubic unit cell is also A cube. Similarly, the volume of the body-centered cubic unit cell is also A cube. Okay, so this is the first parameter we looked at for body-centered cubic unit cell. The second parameter is effective number of atoms per unit cell, which is denoted by Z. So this is also called as number of atoms per unit cell, or effective number of atoms per unit cell, which is denoted by Z. Okay. A BCC cell has 8 lattice points at 8 corners of the cube and 1 lattice point at the center within the cell. As we have seen here, you have 8 lattice point at 8 corners, right? 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 lattice point at the 8 corners, and you have 1 point at the center of the body, right? So this is body-centered or BCC cubic unit cell. Okay. So a BCC cell has 8 lattice point at 8 corners of the cube and 1 lattice point at the center within the cell, right? As shown in figure. There are no points in the face. There are no points in the face, right? So this is one face, there is no point. So all the faces, any face doesn't have, so no face has a lattice point. Only corners, 8 corners have 8 lattice points, and there is a point at the center of the body, right? So an atom at the lattice point within the cell belongs completely to the cell, and the atoms at the corners of the cell contribute 1/8 to the unit cell, because each unit cell is shared by, each unit cell has 8 neighboring unit cell. So each atom is going to share by 8 of the unit cell. So each atom is going to contribute 1/8 to each unit cell. Understood? So each unit cell has 8 neighboring unit cells, right? So each lattice point, if you look at here, so there are one more lattice unit cell here. So as we have seen, so there are 8 unit cells, neighboring unit cells. So each lattice point is going to contribute 1/8 to each unit cell. Okay. So that is why here it is mentioned, right? An atom at the lattice point within the cell belongs completely to the cell. So what we are saying is that this center of the body, so this is going to contribute completely but there is the corner atom. This atom is going to contribute completely. So there is one atom per the unit cell, and plus there are 8 atoms at the 8 corners, but each of these 8 corner atom is going to contribute only 1/8, right? So 1/8. So yeah, so now we can calculate the number of atoms or effective number of atoms per unit cell for this BCC, right? So the effective number of atoms for BCC cell is defined as Z. Z is equal to ZB plus ZF by 2 plus ZC by n. What is ZB? Body centered atom, number of body centered atoms. What is ZF? Number of face centered atoms. And what is ZC? Number of corner atoms. Okay, so now for this BCC cell, as we have seen, there is one body centered atom, so that is why it is going to contribute all. So there is one body centered atom, right? So that is 1, plus there are no atoms in the same faces. So faces doesn't have any atoms. So ZF is 0. And corners, there are 8 atoms at 8 corners, and each atom is contributing 1/8 to each unit cell. So 1/8 into 8, right? So 1 plus 0 plus 8 by 8, that is 2. So number of atoms per unit cell for BCC is 2. So Z is equal to 2 for BCC unit cell. What was Z for simple cubic unit cell? For simple cubic, so this is for BCC. BCC number of atoms per unit cell or effective number of atoms per unit cell is Z is 2. For simple cubic unit cell, that was 1. Okay, right. So this is the second parameter we have calculated for BCC, and we have compared with simple cubic units also, right? Okay. So let us look into the third parameter. So the third parameter is coordination number. We have discussed what is a coordination number. Coordination number is nothing but the number of nearest neighbors, right? Coordination number is nothing but number of nearest neighbors. Nearest neighbors of an atom. Okay, so number of nearest neighbors of an atom in a unit cell is nothing but the coordination number, right? So we have calculated coordination number for a simple cubic unit cell, which was 6, right? So coordination number for simple cubic unit cell was 6. So let us see what is the coordination number for body centered cubic units. So in the BCC cell, atoms occupying the corner lattice points do not touch each other. However, each corner atom is in contact with the atom at the body center. Okay, so as shown in the figure, you can clearly see each corner atom is in contact with the atom at the body center atom. So all the corner atoms are in contact with the body centered atom. Okay, as there are 8 unit cells around each corner of the cell, the atom located at a corner would be simultaneously touched by the 8 body centered atoms of the 8 surrounding cells. Thus the coordination number is 8. So what we are saying is that each unit cell has 8 neighboring unit cells, and the body centered atom is connected or touched by all the corner atoms. So because each unit cell has 8 neighboring atoms, so there is the coordination number or the number of nearest neighbors in BCC is 8. Because there are 8 corner atoms, and the body centered atom is, if I am taking this atom as the reference atom, so I am now looking at the number of nearest neighbors for this atom, right? For this block, which is in the black color, so for this atom, number of nearest neighbors are 8, because there are 8 number of nearest neighbors and there are 8 neighboring cells, right? So that is the reason why each one is contributing, and then the number of nearest neighbors for this atom is 8. Okay, so for the simple cubic unit cell, that is 6. For the body centered cubic unit cell, it is 8. So that is the coordination number, which is defined as number of nearest neighbors of an atom in a unit cell. Very good. So we have even calculated the coordination number for body centered unit cell, and we have compared with simple cubic unit cell. Okay, so the fourth one is atomic radius. In a BCC cell, atoms would be in contact along the body diagonal. And from the figure, so I am saying that there is an atom here, there is one atom here, and there is one atom here, and even at the center of the body, center of this unit cell also there is one atom, right? So this, the radius of this atom is R, so this is R, and the radius of this atom is also R, so this is also R, and this is 2R. Okay, so now I need to calculate the radius of an atom, right? So AG square, I want to calculate AG square. Okay, by looking at this AG square, I will be able to calculate the radius of each atom. So I am just assuming radius is R. I am assuming the radius of each atom is R, but I want to calculate what is the value of this R, right? So I am using this body diagonal, which is AG square. Okay, so AG square is equal to AC square. So this is AC. So AC square plus CG square. Why is like that? Why AG square is equal to AC square plus CG square? AG is nothing but the hypotenuse, right? And AC is the adjacent side and CG is the opposite side. We know from Pythagoras theorem that hypotenuse square is equal to adjacent square plus opposite square. That is the reason why AG square is equal to AC square plus CG square. Right. Okay. So now we have to calculate what is AZ, what is CG, and what is AG. Okay. So let us see what is AC. Okay. I don't know what is exactly AC, but I can write this AC as AB. Okay. AB plus BC. So AB plus BC is actually equal to AC. So that is why I have written AC. Right. AC. I am writing it as AB plus BC, because I know what is AB and what is BC. That is the reason why I am writing AC square as equal to AB square plus BC square, and similarly CG square is I am just keeping as it is, right? Okay, here AG is 4R because this atom is old, right? The body centered atom radius is R, but the radius is R, but we are looking at the diameter of the atom because the atom is there at the center. So that is the reason why it is 2R. So R plus 2R plus R. What is R plus 2R plus R? R, the radius of this corner atom, and the radius of the central atom is R, also R, but we are looking at the diameter because it is along the line, right? So R plus R, that is 2R, and plus the R radius of the corner atom. So 2R plus R plus R. So that is 4R. So what is this? This is AG. So we have calculated AG. AG is actually 4R, right? So AG square is equal to 4R square. Right, so AG square is equal to 4R square, and AB is equal to BC is equal to CG is equal to A. Because that is the length. We know that in cubic unit cell all the lengths are equal, and that is what is the condition for cubic unit cell? A is equal to B is equal to C. If you have A here, B here, and C here, all of them are equal, so you can just take it as A. Okay, so AB is A, BC is A, and CG is also A. Now I am substituting here AG square, which is 4R. So AG square is equal to 4R square, and this is AB is A. Okay, so AB is A and BC is also A plus CG is also A. Right. So A square plus A square plus A square. So A square plus A square plus A square. So 3A square. So that is why I have here 3A square. So 4R square is equal to 3R square. 3A square. Sorry, 3A square. Now 4R is A into square root 3. Okay, I am just taking out square here. So that will be square root 3 into A. Okay, so R is A into square root 3 by 4. So that is the radius of an atom in body centered unit cell, right? So R is A into root 3 by 4. Okay, let us compare this with simple cubic unit cell. So simple cubic unit cell, the radius of the atom is what? Radius of the atom is A by 2. Right, A is equal to 2R, R radius of the atom is A by 2. So in BCC, what is the radius of the atom? In BCC, radius of the atom R is A into root 3 by 4. So this is the radius of the atom in BCC unit cell. Okay, very good. So let us now go to the next parameter that we can calculate for this BCC unit cell. So now we have calculated volume of the BCC unit cell and number of atoms per unit cell for BCC, and coordination number and also atomic radius. So the next parameter is packing fraction. Okay, so the packing fraction for simple cubic unit cell we have calculated, it is 0.52. Right, so let us look at the packing fraction of BCC. Okay, so the packing fraction for BCC cells, Z is equal to, what is Z? Z is nothing but the number of atoms per unit cell. So for BCC, number of atoms per unit cell is 2, that we have calculated. And A is equal to how did we calculate this? How did we get this? A is equal to 4r by root 3. So we have calculated radius. Radius is a into root 3 by 4. So from this you can write down a is equal to 4r by root 3. Just take this side. So a is equal to 4r by root 3. Okay, so now volume of the spherical atom. So we are taking all the atoms are in spherical shape. So that is why the volume of the atom is 4 by 3 pi r cube, right? So volume of the unit cell, this is a simple cubic unit, this is a cubic unit cell. It can be simple cubic unit cell or body centered cubic unit cell. The volume is same because for a cubic unit cell, A is equal to B is equal to C. It can be simple cubic or it can be body centered cubic. So the volume is A cube. Okay. So we know what is A. A is 4r by square root 3. So cube of this A. So 4 cube is 64 and r cube by 3 into square root 3 because 4 by 3, right? 4 by 3, 4 cube is 64 and 3 is there because there is a cube, there is a square root, right? So A cube. So let me just write it. Okay, A cube is 4r by square root 3 into cube. Okay, so that is, so this is A cube and A cube is 4 by 3 that, and then that is 464 r cube by square root 3 cube. So that I can write it as square root 3 cube is I can write it as 3 into square root 3. Okay, so that is volume. So now I want to calculate atomic packing fraction. Atomic packing fraction is Z into nu or V. You can take it as small v. Okay, so not here. This is not a subscript. So this is Z into. Okay, let me correct this. So Z into small v. Small v is nothing but the volume of the atom. Okay, Z into V divided by volume of the unit cell. So that is the atomic packing fraction. Number of atoms. What is an atomic packing fraction? Number of atoms per unit cell into volume of the each atom divided by the volume of the unit cell. Okay, so that is atomic packing fraction. And for BCC, Z is 2 and we have calculated, we have calculated that is, V of the each atom is 4 by 3 phi r cube because spherical shape, atom is spherical in shape and volume of the unit cell is 64 r cube by 3 into root. So if you calculate this, so for here, so cancel out all the terms which will go away. Okay, so then what you will get is 5 into root 3 by 8. So r cube will also go will also go, and this is 4. So here 16 you will get here. 4 ones are 4 and 4 14 and so what you will get is here that is 5. So you have 5 here. So 5 square root 3 will come upstairs. So so that is not 4, that is 6. So 1 in so that is 16 and then 2 8s are. So that is 5 into root 3 which is in the here will go to numerator 5 root 3 by 8. Okay, so that is the atomic fraction 5 root 3 by 8. If you write it as in fraction 5 value is 3.14. So 3.14 into 1.732 divided by 2 you will get 0.68. Okay, so the atomic packing fraction for BCC is 0.68. So 68% of the space is occupied by the atoms in BCC unit cell. Okay, so now let us look into the void space. Void space is nothing but the unoccupied space or unutilized space, empty space in BCC unit cell. Okay, percentage of void space is nothing but 1 minus atomic packing fraction. Total volume is 1. So 1 minus what is the space that is occupied by atom. So that is 0.68 for BCC. So 1 minus 0.68, that is 32%. Okay, so 32% of the space is empty space in BCC unit cell. So BCC unit cell, so let us just compare this simple cubic unit cell and BCC unit cell. So simple cubic unit cell occupied volume is 0.52 and this is 0.68. So what is the void space here? Void space is 0.48 or 48% is empty space. In BCC that is 32% or 0.32. So the empty space is less in BCC compared to simple cubic unit cell. So the last parameter for this body centered cubic unit cell is density of BCC unit cell, and the density we have defined here. So density is mass per volume, so M by V, volume of the unit cell. So then M we have defined it as Z into so that is Z into M by NA into AQ. So Z is here for BCC, Z is 2. So 2 into, where M is molecular weight of the material, so 2 into M by NA is Avogadro number, and AQ is the V is nothing but volume AQ. So that is V is AQ. So that is density of the BCC unit cell, right? So for simple cubic unit cell, that is simply, so for simple cubic unit cell density is M by NA into AQ, because Z is 1 for simple cubic unit cell. So we have also calculated density for the simple cubic unit cell, and we have compared with BCC. Okay. So we have calculated 7 parameters for BCC unit cell, which is body centered cubic unit cell. And now let us look at this FCC unit cell, which is face centered cubic unit cell. Okay, now we are going to calculate all these 7 parameters for FCC unit cell. So the face centered cubic unit cell is a non-primitive unit cell, because the number of atoms per unit cell are, here it is 4, right? So FCC unit cell is a non-primitive unit cell, and it has 6 lattice points at the 6 faces and 8 atoms at the 8 corners. So FCC unit cell has 6 lattice point at 6 faces. So this is one face, this second face, third face, fourth face, and this is fifth face, and this is sixth face. Okay, so these 6 atoms are in the center of 6 faces, and 8 atoms at the 8 corners, 2, 3, 4, 5, 6, 7, 8. So these are the atoms located in FCC unit cell. Okay, now we are going to calculate the volume for FCC unit cell. For a cubic unit cell, it is, the condition is A is equal to B is equal to C. So whether it is a simple cubic unit cell, BCC unit cell, or FCC unit cell, volume is AQ. So SC, BCC and FCC. Volume is AQ, AQ and AQ, because these are all unit cells of cubic unit cells. And for a cubic unit cell, all the axial lengths are equal. Okay, so that is the reason why the volume is same, whether it is simple cubic, body centered cubic, or face centered cubic unit cell. Okay, so the next parameter for FCC unit cell is effective number of atoms per unit cell, or number of atoms per unit cell, which is denoted by Z. Okay, so in a 3-dimensional array, unit cell is surrounded by the other unit cell, and while each corner of the cell is shared by 8 adjacent cells, as we know, and each face is shared by 2 adjacent cells. So each face is shared by the nearest. So this face, for this unit cell, there is neighboring unit cell. So this atom is shared by this unit cell, and there is also another unit cell. So each atom is shared by 2 unit cells, whereas this corner atom is shared by 8 of them, right? But face centered atoms are shared by only 2 of them. That is what is said. 8 adjacent cell, the corner atom, but the face atom is shared by only 2 adjacent cells. Therefore, each face centered atom contributes half of its mass to and volume to one cell, while each corner atom contributes 1/8 of the 1/8 to each of its unit cell. Okay, so corner atom is going to contribute 1/8, and face atom is going to contribute 1/2. Okay, so there are 6 faces and 8 corners in a cubic unit cell, face centered FCC unit cell. Thus, the number of atoms effectively contributing to the FCC unit cell, 6 faces and 8 corners to every cubic unit cell. What I meant is that there are 6 atoms at 6 faces. That is why it is FCC. Okay, 6 atoms at 6 faces of the FCC and 8 atoms at the 8 corners of the FCC. Okay, so then the effective number of atoms per unit cell Z is ZB plus ZF by 2 plus ZC by 8. Body centered atom, no body centered atom, right? So there is no body centered atom. B is 0. Face centered atom, there are 6 faces, and each atom is going to share 1/2. So that is 6 into 1/2. Okay, so ZF by 2. And corner atoms, there are 8 corner atoms, and each corner atom is going to contribute 1/8. So 8/8. So totally you have 4 atoms per unit cell in FCC. So for the FCC unit cell, the number of atoms per unit cell is 4. So simple cubic, it is 1, BCC it is 2, and FCC it is 4. So this is number of atoms per unit cell, or effective number of atoms per unit. So the next parameter is coordination number. Coordination number is nothing but the number of nearest neighbor atoms. So in FCC unit cell, each corner atom is in contact with the phase center atom, and it would therefore be in contact with 4 atoms in the XY plane, 4 atoms in the YZ plane, and 4 atoms in the ZX plane. So the coordination number is 4 plus 4 plus 4. So that is 12. So what we are saying is that each corner atom is in contact with the phase center atom. So if we have a corner atom, so this is the corner atom, and this corner atom is in contact with the phase center atom. Okay, is in contact with the phase center atom. So this corner atom is in contact with the phase center atom. This corner atom is also in contact with this corner atom, and this corner atom, and this corner atom is also in contact with the phase center atom. So each corner atom is in contact with the phase center atom, and it would therefore be in contact with 4 atoms. Okay, so each phase center atom is in contact with 1, 2, 3, 4. Okay, so if I am taking phase center atom as the reference atom, so each phase center atom is in contact with 4 corner atoms. So in the XY plane, and in the YZ plane, and in the ZX plane. So in all different 3 planes, the number of nearest neighbors will be 4 plus 4 plus 4. So totally, 12 number of nearest neighbors in FCC unit cell. Okay, so there you have to think about three planes: XY plane, ZX plane, and XZ plane. In each plane, there are 4 neighbors. Okay, if I am taking so if I am taking this as x-axis and this as y-axis, so this is my xy plane. So this is y-axis. So this is my xy plane. In xy plane, the number of nearest neighbors are 4, and in ZX plane, so there is one more plane. So there are 3 planes, right? So if we draw this coordinate axis or crystal axis, so x, y, z, so x, y, z. So in this plane there are 4 neighbor atoms. In this plane you have 4 neighbor atoms. In this plane there are 4 neighbor atoms. So completely there are 12 number of nearest neighbors in FCC unit cell. So in simple cubic unit cell there are 6. In body center cubic unit cell there are 8. In FCC there are 12. Okay, coming to the 4th parameter, which is atomic radius, following same as BCC. Now we are again taking the body phase diagonal. Okay, atoms are in contact with the phase diagonal of this cube, because this is FCC unit cell. In BCC we have taken at body diagonal, but in FCC we are taking along the face diagonal of the cube. Okay, so again the radius of this atom I am considering as R. Radius of this atom is R, and the radius of this atom is also R, but now it is along the atom. So this is R, and this is also R. So R plus R will be 2R, right? So this will be 2R. 2R plus R, that is 4R. So AF is 4R. So hypotenuse square AF square is equal to AB square plus BF square. Okay, so AB square plus BF square. Hypotenuse square is equal to opposite square plus adjacent square. Adjacent square AB square, opposite square BF square. So that is 4R square is equal to, this is A and this is A, because all lengths are equal. So A plus A, so that is 2A square. Okay, so R is A by 2 square root 2. Okay, so the radius of atom in face centered unit cell is A by 2 root 2. Okay, so yeah, so in a simple cubic unit cell, radius is A by 2. BCC unit cell radius is A into root 3 by 4. In FCC it is A by 2 root 2. Okay, so the next parameter we will look at is so that is radius for atom in FCC unit cell. So the next parameter is atomic packing fraction. So atomic packing fraction for FCC unit cell. So Z into V by V. So where V is the volume of each atom, which is 4 by 3 phi r cube if it is spherical shape. Z is number of atoms per unit cell. For FCC it is 4. Volume of the FCC is A cube. Okay. So Z is 4 V by A cube, where V is the volume of the atom, so that is 4 by 3 phi r cube. And A, we know, we have just calculated radius of the atom, which is A by 2 root 2. So from that A by 2 root 2 you can calculate R. From this a by 2 root 2, you can calculate a. So a is equal to r into 2r into root 2, right? So you substitute this a in this equation of volume. Volume is a cube. So substitute values a cube in volume. So what you will get atomic fraction is 0.74. So 74% of the space is occupied in FCC. So if it is, this is tightly packed unit cell is FCC, 74%. And the white space or the empty space is 1 minus atomic packing fraction. So that is 26%. Okay, very small percentage space is unoccupied. Okay. So the density of the crystal in FCC unit cell, again the formula is Zm into Na into V. Z is number of atoms per unit cell, M is molecular weight of the material, Na is Avogadro number, and V is volume. So Z is 4, M is molecular weight, Na into A cube, they are all constant. So this is the density of the unit cell in FCC. Okay, so for all the three unit cells, all the parameters are given here. Simple cubic unit cell, BCC unit cell, and FCC unit cell. There are 7 parameters we have calculated: volume, atoms per unit cell, atomic radius, coordination number, atomic packing fraction, white space, and density. So if you look at this tabular form, you will know all the parameters for these 3 unit cells of a cube. So these are the references. And thank you. So to summarize, we have calculated the parameters for BCC and FCC in this presentation, and in the earlier presentation we have also calculated the parameters for simple cubic unit cells. So in the next presentation we will discuss about another topic in module 1. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.